Hello, I welcome you to my talk. I'm glad that we are in such a huge audience today. My name is Karel, and I would like to tell you something about TPL Dataflow. This library is a Dataflow library built on top of TPL, and it is meant to help you with so-called Dataflow tasks. Maybe you know this name rather under different terms like data streaming or reactive programming. So that's the topic of today and the aim of this library. To help you with moving data from one place to another and processing it in between. This library also should help you with processing the data concurrently and in parallel. It is actor-based and it has full asynchronous. It is fully asynchronous. It has full asynchronous support for async await. You can use asynchronous delegates and tasks, and it is really helpful in what you need to do. It is quite a simple library. It's not as complex as, for example, reactive extensions, but it is really good in what it does. So the advantages of this library are the following. It helps you create robust concurrent applications because it guides you in what you need to do, and it sort of helps you with the correct patterns. It is partially based on functional programming principles. Also, it helps you with parallelization of tasks. If you have some tasks that might be parallelized, then it is really easy with this library. It's basically you say how many tasks can run at once, and you do this. Because of the way the library is structured, there is no need for synchronization locks, so the performance is also better without this locking. It gives you explicit control over the way the data is buffered and over the way the data travels through your system. And also, really important thing is that it allows you to throttle the data flow. So you don't need to overflow your system. You just specify how much you can handle, and that you will handle. This is an abstract image of how the data flow pipeline might look like. I'm not going to use my presenter to show you. I will use mouse. In abstraction, the TPL workflow looks like this. It is composed from boxes and arrows. The boxes here are so-called blocks, and they are the thing that processes the data. And the arrows represent links between the blocks, the connections that the data travels to. So, for example, if you had a workflow like this, you might have some input data, some buffer that, for example, processes some IoT data or the vehicle positions. So you will receive the data as a byte stream. Then you might transform the data to your domain objects, process the data in parallel. That's why there are multiple tasks here. Once all the data is processed, it might be aggregated and again transformed back to a byte array and output. So this is really just an abstract way of looking at this library. Now I would like to tell you a bit more about the components that this library contains. The main component is are the Dataflow blocks. They themselves contain several other components. Usually they are composed from one or more buffers and maybe some transformation tasks. So in general, the Dataflow block might look like this. It has an input buffer where the data coming into the block to be processed is stored. Then it might have some transformation function that takes the data, processes it, and the output of the transformation is stored in the output buffer. This is the most general case and the most usual one. There are several types of these data flow blocks. There are so-called source blocks, target blocks, and propagator blocks. And the best way you can see them explained is again in this image. The source blocks only have the output buffer. So they are the start of your pipeline. They are the thing that generates the messages for the rest of the pipeline. Then you have the target blocks. Those have the input buffer and maybe also some transformation, but they don't have any output buffers. They are the end of your data. And the propagator blocks have all of these. So they have the input buffer and output buffer. So they are the things that connect the start and the end of your pipeline. The blocks themselves may have some properties. For example, it is the block that allows you to set how many operations may run in parallel in this one block, or how many messages the block might process at once. To connect the blocks, you just need to link them. This is really easy. You just call an extension method. Oh, pizza is here. You just call an extension method on the source block and you say, okay, you will link to this target block. The links themselves, the connections also have also might have several properties. For example, they might disconnect after a number of messages go through the connection, or you might specify a filter. So only some messages will be able to go through this link to the next block. Now I would like to show you a really simple pipeline where we can see the TPL Dataflow in action. And the pipeline will look like this. As our input, we will have one so-called transform block, which is a block that takes an input, somehow transforms it, and returns an output. And this transform block will calculate Fibonacci numbers. And the target of our pipeline will be an action block. This is the block that terminates the pipeline. It takes a delegate, an action function, and executes it on the input. In our case, we will just print out the data to console. Okay. And maybe I will decrease the size of text. Okay, so is this fine? Okay, so this is the program that we will execute. What we will do is we will calculate the Fibonacci numbers. So we have a function to do just that. And now we can prepare our pipeline. Like I said, so we will have the transform block and we will have the action block, and they will be connected with a link. So first the transform block will be called Fibonacci, and it is created like this. It's a generic class that takes two parameters. One is the input and the other is the output. And it takes the function that will transform between these two types. In our case, it will take an integer and it will return int64, or long will be in C#. This constructor is overloaded, so you can either pass in a function that is synchronous, just straight conversion from one to the other, or you can pass in a task function. So in our case, we are passing in reality function that takes an int and returns task int64, because we will wait for a bit to simulate a delay in our calculations, and we will calculate the Fibonacci number and return result. Also, we will pass in block options that define how this block actually behaves. In our case, we are using the default values, but we will change those later. So one value that you can see set here is a max degree of parallelism that specifies how many messages may be processed concurrently. The other block, the action block, like I said, will only output the value. So it takes the delegate that receives some value. In our case, it's a long, and will print out the result. After we have these two blocks, we need to connect them just simply with a link, and then we need some way to start the pipeline, to send the data into our pipeline. There are two ways to do that. We will start with the Fibonacci block, and we can either call synchronous method post that returns Boolean value, and this value tells us whether the message was accepted by the block or not, and this is decided by the block. Maybe the message might be rejected because the block is the block's buffers are full, or maybe the block is already completed and it stopped accepting new messages. So those are the reasons why it could return false. The other function, the other method that we might use is asynchronous. It's called send async, and it also returns Boolean, but wrapped in a task. The semantics are the same as with the post method. The difference is that because this is asynchronous, the block might decide to postpone the decision. So for example, if the buffers of the block are full, then the block might wait, and it will accept the message a bit later. So there's a practical difference between these two methods. We will use the send async. Okay, and now our command will be, we will just specify how many numbers of the sequence we want to calculate, and we will send a list of these values into our function. And let's actually start with a 0. Okay. So we're running our program, and we might calculate 5 Fibonacci numbers, which actually, because I'm starting with 0, will be 6, but you should have 0, 1, 1, 2, 3, 5. Okay, so this is the result we are getting. You might see that getting each of the numbers takes 500 milliseconds, because we are actually running the calculation sequentially. So this is not yet something that would really help us with anything. The only thing we are doing, we are actually calculating the numbers in a different thread. But let's see how we might improve the performance. Let's say that instead of just having one task, we might run 8 of them at the same time. So we change this parameter, and we say, okay, we want 10 numbers. And now you can see that the first 8 were really quick, and the rest goes out. Another interesting thing that you might notice, and you might wonder a bit, is that the numbers are still sorted as they should be, even though we are calculating the numbers concurrently. So we would expect that these results will come out in random order. This is because the blocks, by default, they ensure that the messages that go into them come out in the same order, which in this case is useful because we are trying to actually write down the sequence of values as we received it, but this might not be the case for you, for your use case, so you might want to disable this behavior. Let's see how that works. You can set the property ensure ordered to false, and we will run the example again. Okay, now we have 10 numbers, and you can see that they are written out in random order, essentially. So this was a really simple example how you can implement a pipeline with TPL Dataflow that will stay alive for the whole life cycle of the program. Yes? Yes, it's a generic extension function. It checks, yeah, it checks that that the types conform to each other. You cannot just send garbage or something that won't be accepted to the target. So we saw the pipeline that you might want to create if you have an application that processes some data for the whole life of the application. This pipeline would be alive for a longer time, and it will process the messages one by one. But what if we have a different task? Maybe we have the list of numbers, and we want to calculate all the Fibonacci values in parallel, and we want to get the result all at once, and so sort of collect the results. For that, this won't be that useful because we will easily send all the values into the pipeline, but it would be a bit harder to collect them, and it a bit awkward. We would need to find out where which value is the last one that we actually sent into the pipeline, and to not mess up with other people's. So for that, we might define a completely separate pipeline for our own usage, and then throw it away once we're done. And to do this, we need to somehow signal to the pipeline that we are done, and we need to find out that the processing has stopped because it is asynchronous. To do that, there are two things provided in the blocks. There's a complete method, and this method, once called, tells the block, okay, we are done with sending you messages. You should now stop accepting any messages. You should process all the messages you have in your buffers, and when you're done, let us know. And the way the block lets us know is using the completion task. This task does not return any value. It's a task or task unit, and it only tells us whether the block is still running or not. It might also contain an exception, because if in case there's a processing error, then or an uncaught exception, then this will be wrapped in an aggregate exception and set on the completion task, as is usual in the TPL task parallel library. Now, so like I said, if there's an exception during processing, the block will also be completed. It will stop processing any messages, and it will be faulted. This might lead to some problems if we have a longer pipeline and one of the blocks actually fails. For example, Let's imagine that we have again this generic abstract pipeline that processes some data, and there is an error in this aggregate task. What happens now is that these last two, well, I will call them blocks from now on, because now you already know that these are Dataflow blocks. So these two blocks will be fine. They will be there, ready to do their work, and ready to accept any messages. The trouble is that there won't be any messages coming from the aggregate, because the aggregate is already faulted, and it's not processing anything. The tasks, the blocks before the aggregate are trying to process all their data, and they are doing their work until their output buffers are full, because at that moment they cannot actually send the messages further along the pipeline, because the messages are not being accepted with in this aggregate block. So the process tasks will fill their output buffers, then they will also fill their input buffers, because they will also stop processing values once their buffers are full. They cannot do that. They will be just waiting. The same fate awaits the transform block and the buffer block, and your whole pipeline will stop. Now, this is a problem, because you won't see any messages coming through, even though you are trying to send them in, but you might not see any problems. So because of that, you should listen to all the completion tasks of all the blocks that you have here, which is a bit awkward. So luckily there is a way to avoid this listening, and this is called error propagation or completion propagation. How this works is that when you set up the links, you can say, okay, propagate completion of this block to the next block. So in this case, when the aggregate block fails, it will also tell the next blocks, okay, so hey, I have failed, I'm completed. So the transform block will receive the message, it will process it, and it will complete itself and send the information further away. So, and the same goes to the output block. So if you have the whole pipeline here, and then even though you want the pipeline to last indefinitely, you need to await completion on this output tasks, because there might be an error here somewhere in the pipeline, which will be propagated further away if you set it up. Another reason why you might or you should await the completion is that sometimes the applications also need to stop, or usually they will stop, and you want the shutdown of your application to be clean. So you want to clean all the buffers before you actually shut down, if possible. So that's the error propagation. Let's now see a demo how we might use this, and we will check slightly modified example as before. We will again calculate Fibonacci numbers, but now we want all the results to be collected, and we want to print them out at once. So let's say I want 5 Fibonacci numbers, and you can see that now I got a list of the results. So Fibonacci of 0 is 0, of 1 is 1, of 2 the value is 1, and so on and so on. So I can do the same for different values. So the way this works is similar as before. Again, we have a Fibonacci block that just calculates the Fibonacci number, and we have a collect block that collects the results into some collection in this case, a concurrent queue that will be returned once our pipeline completes. I'm using concurrent queue because the action block also might run concurrently, and we need to be aware of possible race condition bugs. Then we can link the blocks. We will send all the values to the Fibonacci block, this time using a different method, and we will complete the Fibonacci block. Now, like I said, when we call the complete method, the Fibonacci block will stop accepting any new messages. It would throw an exception, but it doesn't mean that we have all the values, because they are running asynchronously. So we have to wait for the calculations to finish, and then we will collect the results. And I already showed you how the result looks. Okay. Is this clear? Yeah, okay.
Putting in the queue, or
oh yeah, and queue puts the value in the queue, because there's I don't know if there probably is nothing like well, it's yeah, and queue puts the values into the queue, and then we will just enumerate the results.
you would just use usual queue without the
Well,
not the
I could
queue.
use list.
Just usual queue, not the parallel queue.
You can try, but well, the danger is that probably nothing will differ, but yeah, so there's no difference right now, but this collection is not thread safe, so there might be some problems. Usually, I would use the concurrent queue just to be sure. Yeah. Maybe adding to list is fine. I don't know. There's also an alternative way to get the data from our block, and that is using reactive extensions, because each block, well, not each block, but each source block can also act as a reactive extensions observable, so we can subscribe to it. So alternative way would be not to define the action block, but we could define the observer that will subscribe to the Fibonacci block as observable, and that will add the values to a result list. And here I am using just a normal list, because this runs as single threaded, but that's the way the reactive extensions work by default. Otherwise, the example is exactly the same, and this is actually how you would normally how you might want to connect your pipelines. You might have a pipeline where you need more control, or fine-grained control, where you use TPL Dataflow, and on the input and the output would be observers. So you might you can connect, you can subscribe to reactive extensions observers, and then output also observables on the other side. And this is how we are actually using the pipeline in one of my projects. Okay. Now I would like to shortly tell you something about the various blocks that you can use to create your pipelines. There are many more. I will just mention a few basic blocks. You can find them in the documentation, but I believe that these are the most useful ones. The transform block we already saw. It's a block that will take a value of type A. It will somehow transform it to type B. In a sense, this transform block corresponds to LINQ select or map in F#. Depends on the vocabulary you are using. So there's nothing really that strange on this block. Because we have a select block or transform block, we will also have a transform many block that takes a value and generates I enumerable of different values. This might be used for filtering, or also there are other interesting applications which I might tell you later. There's a broadcast block that you can use to implement splits in your pipeline, because by default, if you connect a block, a source block, if you connect it to two targets, then only one of them gets the message. It works the same way as task queues or worker queues. So the second one is ignored. If you connect two blocks, then the second one, the first one always has priority. So the first one will get the message if it can. If it cannot, then the second one will get it. If you want
buffer or
exactly, if it has full buffer or for some reason does not accept the message. So if you want, if you have a value and you want it to be processed in several different ways, in different blocks, then you will use this broadcast block. And you might notice that its output is not A, but like A with this apostrophe. This is because the broadcast block knows that the next blocks might mutate the values, and that would be a danger because of the concurrency in the blocks. So what you should do is to copy the value, to make several copies of A and send them to the different blocks. And the broadcast block itself accepts a delegate that should copy the value or clone it. Another type of block, once you have all the calculations that you split, is a join block. This block has two targets, so it will accept values of type A or B, and there's an overload that will accept A, B, or C, and it will generate a tuple of these two values. The interesting thing is that if you are doing different calculations, you need to make sure that you get the correct values. That they might be, the A and B might be different results from different blocks. So this is, but this is what is ensured by default because of the ordering in the pipeline. And I will show you an example. Yes, it will wait. It will never generate something like A and null or B and null. It will wait, and when it can generate the tuple, then it does. Otherwise, it does not consume the message.
There comes like lines of A's and lines of B, like, right?
Exactly.
Pairs them, like zips them, or
exactly. It works the same way as a zip. There's another type of block that does sort of greedily takes the values and generates tuples if it can, and if it can't, it just would create A and null or something like that. But that's a different type. Now I will show you how these blocks can be used. So we will create the pipeline that looks like this. The input will be again an integer number, and it will be broadcast into two blocks that will calculate two different sequences. One will be Fibonacci sequence, the other will be so-called Lucas sequence, which is the same as Fibonacci, only starts differently. I will show you. These values will be joined, and output. Okay. So block samples here. Okay, so first here is the implementation of the Lucas numbers. You can see that it's almost the same as the Fibonacci numbers. The only difference is that Fibonacci's start with 0 and 1, and then each next number is the sum of the previous ones. The Lucas numbers start with 2 and 1, and each is the sum of the previous ones. So it's almost the same, but has different properties, different ways to work. And this is how we can define our pipeline. So, like I said, we will define the broadcast block, 2 transform blocks, and join block. The broadcast block accepts a function that will create a copy. For integer, we don't really need to create a copy since it's struct. The Fibonacci block will calculate Fibonacci numbers with some delay. For now, because right now, because we want to make the application a bit more safe, we will not return a tuple of integer and long, but we will return a Fibonacci value, which is let's call it like this data structure, because I assume mostly C# developers are listening, that contains the index of the Fibonacci and the value, and the same for the Lucas numbers. Okay, so the Lucas block is generated similarly with some different delays that will come in handy later. The join block just takes values of different types and generates tuples, and the output block will take the tuple and print out the value. So this is our whole pipeline, and then we will link everything. The only interesting thing with the links is that the Fibonacci block and the Lucas block, they both link to the join block, and the join block has 2 targets, has target 1 and target 2. Okay. So if we want to generate 5 items, we will get these items, well, 6 of them, of course. And this will be the pairs of the sequences. So 0, 1, 1, 2, 3, 5, 2, 1, 3, 4, 7, 11. Now, 2 targets, because this is, where's the join? This is the target. Target is where the message is being sent, and source is where it's being produced. That's how it's called. So the join block has 2 targets, like target 1 and target 2. Okay. Now I want to show you also. We already saw what happens when we don't order our data, and we calculate the values concurrently, but this is much more dangerous, of course, with the join block, because we will also mix and match the values of the sequence. For example, here we might get Fibonacci, or the 0th Fibonacci and the 3rd Lucas number. So these results would be completely meaningless to us, might be. And another thing that I would like to show you is what happens when we have a capacity of buffers that's lower than the number of values that we want to calculate. So here we set the bounded capacity to 10, and this is the capacity of the messages that are stored in the buffer. and we will request 20 numbers. Actually, let's do it like this. Let's do it in order so we can better see what's happening. Okay, so 20 numbers. Okay, and you see that we received the values from 0 to 9, which is the 10 values, and then only the last one. And the reason of this is a property of the broadcast block that I didn't tell you about. You see, the way the broadcast block works is that it has a buffer of 1. It only ever contains one message. And when it receives a new message, it will drop the previous one and send the new message to the next blocks in line. But if the next blocks are full and they reject the message, then the broadcast block doesn't care. So what happened for us here is that it received and broadcasted the 10 messages that we sent to him that were fine, and the 11th, the one with the index 10, he tried to send it to the other blocks. They rejected it, but the broadcast block immediately received a new message, and so he dropped the message with index 10, tried the same with index 11, and so on and so on. So that's why we calculated the first messages that were fine, and then the last one is also calculated. Oh yeah, because that stayed in the buffer of the broadcast block. So this is something that you need to be aware if you want to broadcast messages, if you want to duplicate the values, that if the flow of data is higher than what your pipeline is able to process, then you will be losing messages. And there's a way around this. I don't actually have an example, but it is possible to work around this with using transfer many block. What you can do is, instead of the broadcast block, we could use the transfer many block, and we would just create 2 copies of the integer, and we would say, okay, this one goes to the Fibonacci block, and this one goes to the Lucas block, and the links would filter out the values, so they would each get one of them. But this transfer many block would store the remaining values in the buffer. I think it was a mistake that I didn't prepare an example for that, but I will show you a different way to solve this problem. Okay, so that's this thing. So the thing I just described, the fact that the broadcast block is throwing away messages, is called load shedding, and it's one of 2 ways that you can react to a higher load than you are able to process. And sometimes it might be the thing you want to do. Sometimes you are just displaying statistics on some online dashboards. So then who cares if you lose a few messages? It doesn't really change what you want to display. But sometimes you don't want to drop messages. Sometimes you need all of them. In that case, you should avoid the broadcast block, and ideally you should apply a so-called back pressure. That means that when you have too much data in your pipeline, then sorry. If you have too much data in your pipeline, then you stop accepting data, and you sort of tell to your producer, okay, don't give me any more data. And your producer in this case does not mean an external system, but rather some component in your system that loads the data from outside. I'll show you how to do how to apply the back pressure from the point of TPL Dataflow. That's here. So the way to do this is really simple, and we already touched the properties at the beginning of the examples. Back pressure just means that you will not accept any new messages, and to do that means that if you are sending a new message to your pipeline using the block post, and your message is either enqueued, which is fine, or it is rejected. And in that case, you should wait for a while. We are here just sleeping for a second, and then try again. So in a way, this means that you sort of buffer the data somewhere else. That might be an external system. For example, if you're working or reading data from RabbitMQ or Kafka, you just don't read any more data, and you process them a bit later. And also at this point, if you wanted to drop the data, then you can do it here. You don't need to use the broadcast block for that. So to show you an example, we have a pipeline with capacity of 5 that runs sequentially, and we want to generate numbers from 1 to 10, and we want to get all of them. So we will post the values with back pressure. Pressure load shedding. So now we should see that 5 of the numbers will be enqueued, and then the rest will have to wait. Okay, you see that 5 were enqueued, then the buffer is full. We will wait with the further work, and once there is some space in the queue, we will send a few more numbers, then wait again, and so on and so on. So this way the pipeline will run all the time, but we will not lose any numbers. And takes that time. Okay, any more questions? Not yet. That's it from me. I just wanted to show you really basic examples, but if you're interested, I have 2 links here to really interesting and much more involved examples on the internet. One is from Jack Van Leite, and it describes a way to process some sensor readings from some machinery, I don't remember which, and it reads 1,000 of messages per second, and somehow processes them, feeds them into different applications and dashboards, and stores them to data. And it's actually a series of articles where he handles this use case with different technologies. So he has 2 examples of how to use TPL Dataflow, and 1 example how to use reactive extensions for this problem. He promised a Kafka example, but that's not there yet. And another example is from Ricardo Terrell, and this is an example of how you can process a large stream of data. He takes a file that has 1, 2, or 4 gigabytes, and he needs to, well, the idea is that he needs to compress, encrypt, and transfer this through a network. So this example shows you how you can chop the file into different chunks, how you can compress the chunks in parallel. Then you will encrypt them, and then you will send them send them over a network, and also shows you how you can aggregate these. This is a really interesting example that shows you how you can use TPL Dataflow to improve performance in quite an easy way.
On different machines somewhere else there.
In the demo, it's on the same machine, but
This library like supports this aggregating this, or
not really. That's why he uses reactive extensions for this. You could do it in a manual way, but it's not meant for this, because the TPL Dataflow, the blocks are supposed to be stateless, unless it's the target block. So these are stateless, and this is stateful, and but he uses reactive extensions for that. He uses some scan method, I believe. But I think it shows quite well how you can integrate these two technologies and play with the strengths of both of them. Because the thing is that I believe everything that you would implement in TPL Dataflow, you can also do with reactive extensions, but it's a lot of time a bit awkward, because the library is built for something else. But that's for a different discussion. You will find the talk on my GitHub later, and I have the links here. So that's it from me. Okay. Questions, answers?
There are no.